I'm scheduled to be started already, right? I have 3 minutes before I need to start?
No, you started 3 minutes ago.
I am on the ball. Okay, you guys ready?
Yeah, let's do it. Go!
Okay. Hello, my name is Brock Wilcox, A-Wade on the internet. Like that. You see me all over the place as A-Wade, it's very common. Hi, Scott. Hi, video people. Hi, Beth. Hi, every people. Which one? A-Wade, a word whose acronym is its definition. Thanks, that's good. So, today's talk will be fun, I hope. We're going to build a software synthesizer in about 20 minutes. I've done this talk twice now, once in 20, but it took 40, and once in 5. That was weird. I wanted to start with a little bit about sound. Not too much, because if we start going off into consciousness, then that's a whole psychology thing. But what we can start off with relatively straightforwardly is speakers. Oh. Sound. Sorry, bear with me. There we go. All right, this is a speaker. Speakers are physical devices you may have seen before. They move back and forth like that. You've seen hertz before. Hz is just cycles per second. It's literally how many times it's moving back and forth. This one's slowed down, so you can really see that a speaker is just moving back and forth. That's all that it's really doing at all. If any of you have ever taken apart a speaker, if you haven't, I highly recommend it. But I used to take them apart all the time when I was a kid, much to the chagrin of adults and things. They have this, at least older ones, there's a lot of different types, but the good ones have this big old permanent magnet. Really fun, you get some sand, you get lots of bits and everything. And they also have this metal coil, which is an electromagnet. And all that really happens is these two little ends of the wires hook up electricity to them, usually an alternating current, and each time you throw some electricity through there, the electromagnetic pulls toward the permanent one or pushes away from it, just moving the whole thing back and forth. A really good visualization of this is to actually turn it sideways, believe it or not. You can actually see it pulling. Yeah, animation is cool. Because that way, the up and down corresponds with the electricity that's going through here. Here's a picture I got from Google where it's going from plus minus a volt. And you could actually see like a nice wave, or if you were playing some sound file, you might see a lot of these wiggly line things. This is a direct correspondence between the electricity going through, the movement of the speaker, and back on the other end, the things that we're actually kind of sending to the speaker, if that makes sense. So it's kind of a one-to-one correspondence between all those things. And it's actually really fairly simple, which is not always the case whenever you're dealing with things. So the shape of this wave, the electricity going up and down, affects what things sound like. So I have a couple simple examples of that. This is a sine wave using Audacity. We can just zoom on in here. Where's that zoom button? Yeah, it goes up and down. That one's pretty boring. We can actually play it. Nice. Oh, don't save changes. Here's a more interesting song. Let's zoom in again. So we get a little wave looking. So you can actually see waves. See that? Lots of up and down things. And those up and down, if we had like, one of those cameras and we could actually see my thing, you could actually like reverse engineer what the wave was by videoing the speaker, which is pretty cool. So there's a couple things I wanted to point out about the shape of these waves. This is the most important two things, is that when these waves get further and further away from the baseline, basically no electricity, the higher they get, the louder they are. So whenever it's really close like this, not very loud, higher loud. This one's a lot harder, this pitch stuff. The speed at which it goes back and forth, the wiggle speed, the number of cycles, indicates the pitch. So if it goes back and forth really fast, it's going to be higher pitch, like a beep. If it's really low, it'll be beep, stuff like that. So what we want to do, though, is make this into the digital realm. All that we really need to do here is take our wave and slice it up. Sound cards do the work of actually translating this into electricity. We don't have to worry about that. So we'll divide this wave that we get evenly in time into samples. You'll see them more in a second. And we each sample, each point on the wave, we're going to say is just a floating point number from -1 to 1. And yeah, evenly spaced over time. So if we go back to my example here, and I should have memorized the shortcuts for these. Awesome. And we zoom in a little further, you can see there are actual points. These are samples. And if you pay attention on the left, there's a nice little line from -1 to 1, which I ignored until I did this talk. Now you can see it, which is pretty cool. And if I were to just scroll, you could actually see the line going up and down. And what I was saying about the shape of the sound kind of affects what it is. If we go back to my previous one here, we zoom in far enough, we also get samples here. But the waves are very, very different. And the shape of the wave really is determining that we get this, discotheque instead of a boring beeping sound. Now, the important thing, the cool thing, is that there's still only one sample at any point in time. No matter how complex my sound is, there's just one, and it's just doing more and more complex things. So some terminology real quick. Samples per second is called sample rate. So here's some common ones. CDs are a really common one, 44,100. That means there's 44,100 individual, basically floating point numbers in every second of sound, like from a CD. The other thing that people talk about is bit depth. This is just the representation of the up and down. This could be kind of the granularity of the volume. If you're doing 8-bit, then you only go from effectively dividing it up so that you have 127 below 0, 127 above 0, so you can't finally distinguish between really, really quiet sounds and really loud sounds. I looked it up. Human ear, 21-bit, 40,000 samples a second. It's because humans hear at about 20 hertz is the highest pitch that most people can hear, and you need kind of two samples, one for the up and one for the down. Anyway, so we just got to generate these things. 48,000 samples a second. That's what I'm going for. Not too bad. No problem. We're very spoiled by modern hardware. There's a really cool library named PortAudio, which just flattens out all of the dealing with the hardware stuff cross-platform. Somebody wrote Perl bindings. And there's some alternatives. You could pipe directly to raw sound cards if you want, or other high-level software. You could generate a WAV file and play it somewhere else. We're not going to do that, though. This is some gibberish for getting it going. The important part is that I get a stream that's connected to my sound card, and I also told it to go at 48,000 a second. Some buffering junk. And then all I have to do is loop forever, build up the sample, and then write it. We'll go over this a little more in a second. The only weird thing is this pack, where I'm actually turning it into a real floating point. Uh-oh. That's what you get for not testing your talk. Awesome. Okay. This is the only important line in here. Sample, rand, all the rest is boilerplate junk. So we're just saying samples are random numbers. You've probably heard static before. Here's another one. I do have an exit if time is greater than 1 here, so hopefully this will... Yes. So this is another example. My sample line in this is really the main thing that's changed. And it's this little sine function, which if you throw into a graphing calculator will give you a sine wave, just simple going up and down, 440 up and downs in 1 second. What about 2 beeps at once? Turns out all you have to do, remember, in the end, you only end up with 1 sample at any point in time. So if you have 2 waves and you want them to play at the same time, you just add them up. You can literally add the sample, that floating point number, at the same point to the other, and you get something cool. So I'm adding just 2 simple sine waves, and you get that. We could listen to it. Sounds like a little phone. So the only thing different about these two is they're doing it at different frequencies. They add together, though. So I got all this working just in a plain script, but I decided I wanted to generalize it a little bit. What I want is to be able to call a function called getNextSample, and it just gives me a sample. Just call this lots and lots of times, 48,000 times a second, and new sample each time. Here's one way we can do it. Really simple. You call sine, and every time you call it, you have a global for the time, which something else will have to increment. But each time you call it, if time is changing, it's going to give you back the current sample at that point in time. That was easy. No problem. You call these generator. The part that I think is important about the generator, it's kind of a stateful function. Other languages additionally have some syntax which make this a little bit different, but we're not going to worry about that. Not that fun because you can't really change it. You have one and it's just stuck where it is. What I really want is to be able to parameterize this. So I want sine to be a generator, which is even better than a regular generator. And it'll give me back a generator, and then I call that over and over again. So if I want a 440, I do that. If I wanted, I could call it with a different parameter value and get a different generator out of it. We can do this easily. We'll use closures. This is a great, simple example if you want to learn about closures and subrefs and things. We're going to get the frequency from the input to sine, and then we're returning an anonymous sub here. And we still use time as the global, but we have frequency, which was passed in. And it just stays whatever it was that was passed into us. So then we can call it, and then I wrote a subroutine named play, which, given a generator, just sends all of this stuff to the sound card. And that's what it would look like. Sweet. All right. We can do at least one more thing, which then makes this really fun, which is we can use generators as the inputs to other generators. So I wrote this thing called generalize because I still want to call it with constants as well. All it does is if it's a constant, it turns it into a generator. Implementation detail doesn't matter too much. But with this, what we can do is we can say make an LFO, which is a low frequency oscillator. Sine wave goes really slow, 5 times a second. And then we can make this little generator that calculates a frequency from that. So sine wave is still going to be a number from -1 to 1, multiplied by 100. So now you're going -100 to 100. Add 440, so we're going from 340 to 540. And then we pass that in as the frequency to a sine wave. So when oh, good. Okay. So you can hear it, instead of just having one frequency, it's having a frequency that is dynamically changing over time. I threw these into a library. The point wasn't really to make a library for other people to use. The point was to make weird sounds. And I hope to inspire you to do similar things, not necessarily to use my library. My library is there so you can pick it apart, change it, fork it, maybe add more stuff. So here's an example usage of it. All right, we can go better. It plays forever whenever I don't have mocked up examples. So we can make this thing called an envelope generator. I stole this from my Commodore 64 manual, I think. The idea is that instead of just running at the same volume the whole time, what we'll do is we'll make a generator that acts as a filter. and it just scales the wave. Remember, when the wave is at 0, it's going to be silent, and whenever it's at, you multiply it by 1, it's just where it was before. So the idea is over a short period, we multiply it by an ever-increasing number until it gets to full volume, then we wait a while, and then we decay over time. I didn't do the decay, I just did attack, sustain, release. So I made an envelope generator. You give it a generator, and it applies this to it. One really cool thing is whenever it gets to the end, when it gets to after the release, it returns an undef instead of just returning zeros forever. This helps us because we can then make a sequence generator. The idea here is if we have a couple envelopes, we can say play that one until it gets to the end, and then play the next one. It's pretty straightforward. We could do something similar where we do a combine generator. If I have time in a second, I might show you some code for some of these. But the idea is you give it a list of generators, and it will take the first sample of one. Remember, every time you invoke one of these, it just gives you another floating point number. And you invoke it again, it gives you another floating point number. So the combine generator takes one sample from the first generator, one sample from the second, adds them together, sends them off, and then just keeps going. Very stateful. But we can do something even more fun for the purposes of this demonstration, which is that I have a touchscreen, and I have a command called X mouse position, which will tell me where my mouse currently is. And I can split that to get an X and Y coordinate, and I can take that X and Y coordinate, and my X coordinate, I don't know what I have, 1024. That's actually not too bad for music. I could say that's the frequency. Go from 0 to 1024. I also have one that does up and down. Maybe we can do some volume. So here, check this out. Oh, I have an amp that all it does is multiply the output of that generator by the amount. So I made a generator, which you just saw, called mouse frequency. Ultimately, it outputs the X position of my screen. Some of this is for efficiency, so it doesn't call X mouse position all the time. It only calls it every 1,000 samples. And then I multiply it by a similar routine called mouse volume. And now we have a synthesizer. Let's see if it works, shall we? So it's awfully fun. Thank you. So we have, oops, that's not the right one. Where are we at here? So that is the technical end, but I do actually have a little bit of a bonus. Real quick, here's some links. They'll be in the slides. And there are other things that actually do this. Sort of, they make a DSL language out of the same concepts. There's a lot of other projects. The Wikipedia has a bunch. But what I really want to show you, since I have 2 minutes, or actually I probably have less than that, but it's lunchtime, is that thing is called Looper, you might notice, because I can make it record little loops. And it's skipping because my buffering's bad. Alright, so now I have it set up so that if I do a capital letter, I can make all kinds of horrible sounds. So the idea is every time I press a button, it's starting to record a loop. And then whenever it's done, it goes back. So let's look at it, shall we? Just real quick like. Here's my mouse frequency thing, and here's my mouse volume thing. But I also have one called Looper, which is just another generator, and it uses a read key to look for some keys on the keyboard and keeps arrays of samples, is all it's really doing. So ultimately, the end one is similar to the previous, except I have one extra layer in here, and I can make crazy loop stuff. So I highly encourage you all to, go forth, make crazy sounds, or just anything that's awesome. Thank you very much. Do you have any questions, comments? Question in the back. I have not tried this on other ones. There shouldn't be any problems. NoiseGen, PortAudio itself runs on Windows, Mac, and Linux. It binds against all 3 sound platforms, so it should work on other ones. Yes? So the question is, how quickly do you get to the point where this doesn't work anymore because you're calling too many functions and it's too slow? Well, you heard it skipping a little bit earlier, so I've already hit that point. I'm running it at 48,000 samples a second. You can down that quite a bit and still have lovely noise-making abilities. I originally wrote this using Coro Generator, where you could write some even crazier things, but the context switching was way too slow, and I couldn't do hardly any. With my current implementation, I ran it with, I think I was up to like 15 or 16 waves all at the same time, and it was not really a big problem. That's one huge advantage of people who have actually done this a little more formally with a nice language or something. You can optimize this in a lot of different ways. I was seeing how far I could get with just using regular Perl things, and surprisingly, it worked pretty darn well. Any other questions? No? Okay, lunchtime. Thank you all very much. Shout out again to Beth if you're watching. You like it?
Well, I went to Miyagawa's talk, and I was like, this talk that you just did is the one.
I have one more thing. I'm sorry. Miyagawa's talk reminded me. I actually ported this to Ruby and presented it at the Ruby group over near where I live in Arlington, and I have a Python port. I had to write PortAudio bindings in order to get it to work in Ruby. So anyway, share and share alike. Okay, sorry.
So yeah, I saw Giles Focus do like, the similar thing with generators and all that stuff in Ruby for Epidactyl or whatever it's called.
Nice.
And so like I wanted to do this like 2 years ago and could not figure out an audio library that would work. So I thought, I'll just port the Ruby bindings, and that's like a huge ordeal with this XS versus their stuff. Anyway, this is awesome.
Yeah, I can.
So
and I can. If you wanted to do stuff with the Ruby, I can get you the working bindings. I had to find them.
I'd rather use Perl.
All right. Yeah, it works
But,
great.
yeah, that's awesome. So I will definitely play with it.
Thank you. It's very fun.